cosine of pi times n. So this is n times pi over 3, and this is n times pi. So that's the two frequencies you're talking about. A frequency that's at pi over 3, which we got labeled over there, and you have another sinusoid that's at pi. So the one that's at pi is going to disappear because its magnitude is going to be reduced to 0, because that's what the transfer function says is going to happen to a frequency that's at pi, at omega equals pi. And the other one is going to have its amplitude increased by a factor of 10, and it's going to encounter a phase shift of minus 58.2 degrees. So y is the filter BAX, okay? And you remember you had this filter function from way back that would take the impulse response that has a numerator of b, a vector b, and a denominator of vector a, and some input x. And this filter function will convolve those two things and generate the output for you automatically without you having to do anything. All right? And MATLAB will do that for you. So that will generate the output, okay? So MATLAB does that, okay? And then, what else is? So we did that. So we did 200 samples. So we did that. We used that as an input of the filter, got the out. And now we want to plot the input and the output of the filter using subplot. Okay. So again, you use this kind of deal over here. So now you want to subplot 2, 1, 1, and you want to plot, in this case, stem. All right. All right. And now you want to plot the input and the output where it's steady state. Okay, so when you put an input into a filter, the filter is initially relaxed. That means it doesn't have anything in it. And so in order for the filter to operate, it has to receive lots of samples, and then it finally, due to its feedback and everything, it settles down to a steady state output. The first part of the output you see is the transition, is where you have the transitory response. And then after so much time, you get into the steady state response where the transients die out. So it wants to plot this steady state. Does it say plot the steady state? It doesn't. So anyhow, you plot the whole thing. It doesn't really matter. You can plot n of x, and it'll do that. And then subplot 2, 1, 1, 2, 1, 2, right? Stem y, n of y. Well, I don't need those things at the end anyhow, right? So now you'll get plots of the input x and the output y. And what you see is, and sometimes you don't have to plot all of n, because the first part of n, it isn't doing anything. You got a lot of transients there. You don't really see anything. When n gets large, then you start seeing the steady state response, and you see what the output is for the filter for large time values. So sometimes instead of plotting all of n, you only start plotting when n equals 100. You go from 100 to 200 rather than 0 to 100. Rather than 0 to 200, because the first part isn't worth seeing. But if you do that, then you know you'd plot 100 to 200 x. Well, you got to plot that at 100 to 200 too. You need to 101 to 200. Yeah, and then if you did this down here, you'd have n, and it would go from 100 to 200, and y would go from 101 to 200. So there are 100 points in that range, and there's, well, let's go 100 to 200. No, Now you have the same number there as you have there. If you don't have the same number there as you have there, get an error. It won't plot it. Anyhow. So this is plotting what's late in the game and looking at the output. And if you do that, you see the input. You got a plot up here, and you have a plot down here, and you have a plot, an input plot. And if you want to use SIM, you see a lot of dots. I don't know. Well, if you use plot, well, maybe plot's easier. I don't know. It's easier to draw for certain. If you use plot, then you see something that looks like I don't know. It goes all over. It looks like that. That's the input, because that's this thing. The sum of those sinusoids. But on the output at 100 to 200, this is 100 to 200. Well, make 200 here. Make this 200. Okay. On the output, all you do is see the value of this function right here, because this one's reduced to 0. You only have this one. And so this thing is increased, its amplitude's increased by a factor of 10.2, so now it's 10.2 up here, and you see it go like this. Okay? Okay? And so you see a single sinusoid. Okay? And what did this filter do? This filter removed the effect of that sinusoid. It canceled it out, removed it from the signal. So it was here in the beginning on the input, but when you look at the steady state response of the filter removed this sinusoid, because it put a 0 right at, pi, right where this frequency of this thing is. So its response, the amplitude response or the magnitude response is 0. And so it gets rid of it. And all you're left is with the sinusoid, and when you do the plots, you'll see that. You see it happen. This is this way, because that's a vector, so you want those points. Well, it doesn't really matter, I guess. So I don't even know why they even do this up here, because you don't really have to do that, because you don't care what that is. All your plot is the output. Well, I guess you need it for this. You need it for this. But you need it for the input so you can get the output. But when you're plotting the output again, you're only plotting the later part of the output, so you can see that the original sinusoid is removed. If you plot the whole thing, you see the first part is all jumbled. The input looks the same, but the output looks jumbled around here, and then finally the filter has its desired effect after the transients have passed, and it turns into a single sinusoid at pi over 3. So that's that one. All right, so that's that case. So here's a trickier one. Yeah, well, it's not that tricky. It's a tedious example. So this follows. The next one follows the example in the book rather straightforward. So it is 5.3. Well, yeah. If you written that down, you remember what occurs in MATLAB.